So this week's lab continues the study of enzymes. We're still using catalase, yeast catalase, as we did last time. And rather than doing substrate concentration, which remember the substrate is hydrogen peroxide, rather than testing the effects of substrate concentration on the rate of reaction, we are going to test the effect of temperature on the rate of the reaction. So if you remember, molecules are in motion. So when you have a test tube with peroxide in it and yeast in it, that peroxide is in motion as long as you're not at absolute zero. And it's hitting the yeast. It's probably actually popping some of the membranes of the yeast and getting into the yeast because it does oxidize things. And then it's interacting with the yeast catalase. And then it liberates oxygen when that happens, and that's how we measure a change in pressure. Now, the warmer a test tube is, the faster those molecules will move, because temperature literally is a measurement of the movement of molecules. The more molecules are moving, the warmer something is. So the warmer things are, the more often catalase and hydrogen peroxide will smack into each other. And of course, they got to hit each other just right at the active site and the peroxide, but the faster things are moving, the more often things will bump into that active site, and the harder they'll bump into that active site. So there's activation energy provided, and things are moving fast when things are warm. Now your peroxide, I don't know if I mentioned this last time, it will go turn into water and oxygen all by itself if you just add activation energy to it. It's a somewhat unstable molecule. That's why it's sold in brown bottles, because sunlight is enough to get it to start changing the water. So we'll want to keep that in mind. Just if you're near a window, maybe keep if you have peroxide poured into a clear cup, keep it on the shady side. All right. So Dr. Runge, let me try to remember his example of this. The last time we looked at substrate concentration. So think of it this way. Molecules react when they bump into each other. So if this were a dance floor, and there was only, and it's during a pandemic, and there's only, 7 of us in here or something, and we're all dancing, let's just say slow dancing here, real slow, we're dancing around. What are the odds you're going to bump into somebody? If it's fairly empty and you're dancing slow, not that likely. That's, so that's a low substrate concentration. Now we could speed up the odds of you bumping into somebody if we sped up the intensity of the dance, even if there were fewer people in here. You're a little more active, you're moving around a lot more, you might bump into somebody. Now, if we add a whole lot more people into the room, there's a good opportunity then they'll bump into each other. Now this week, rather than adding more molecules into the room, right, more molecules into the test tube, we're keeping yeast and peroxide at the same concentrations today. 3% peroxide and the same concentration of yeast you made last time. So you might have to either check the manual for this week or just go back to last week to see how you made that. Make it up just like last time. You're going to test 5 different temperatures. So this is like maintaining the same number of people in the room, but changing the temperature. You're going to slow down the dance. You're going to speed up the dance. You're going to change the rapidity of collisions by making things go faster or slower to see if you can actually see a change in the rate of the reaction. And of course, if you get really warm, that could have an effect beyond just the speed of which things are colliding. And we'll talk about that in a second. So you're going to pick 5 temperatures between 4, that's just above freezing, 0 is freezing in Celsius, recall, between 4 and 60 Celsius. You're going to pick 5 temperatures. Be sure to treat all groups as identically as you can. Same incubation time. So by incubation time, I mean how long they're at a certain temperature, things like that. Once you reach the target temperature that you're going for, so let's say you want to have a test tube at 60 degrees Celsius. You're going to turn on your heat block, which are the big boxes at your bench today. Set it to 60. It's not going to be at 60 instantly. You're going to have to monitor it. And once the test tubes in there get up to 60, then you're going to set a timer for The manual, in the past I've done 5 minutes, but we're trying 1 minute this semester. So let it sit at temperature within 3 degrees of your target temperature for 1 minute. So it incubates there. That's what we mean by incubate. It sits there at that temperature for 1 minute. Then you're going to mix the peroxide and yeast together while they're still sitting in that heat block and see what happens. So one way the students sometimes mess this up is, especially when we used to do 5-minute intervals, is students would start the stopwatch as soon as the test tubes went into the heat block. Well, they're still at room temperature when they go into that heat block. You got to wait till they're warm. So you're going to have a thermometer in one of them to watch it. Okay? We'll talk about that a bit more. So let me just walk you through here. The research question basically is, what is the effect of temperature? What is the effect, or what is the relationship between temperature and yeast activity? And there's an additional component to that in the manual. It says, basically, I'll paraphrase, it says, and how does that relate to the survivability of yeast in the wild? And this actually ties into what Bio 2 is doing this week, and last week, and then next week. They are doing an experiment on homeostasis, on thermoregulation, how organisms can maintain a constant body temperature. Like how does a snake maintain constant body temperature? And we have to do homeostasis. You know, we sweat when we're too hot, we shiver when we're too cold. A snake can get into the sun, crawl out of the sun. You know, why is that so important? Well, it's important. One of the reasons is all of these enzymatically catalyzed reactions that keep our metabolism going. We have to have the right temperatures for them to work. So these are things to think about, like what's the point of studying temperature and enzymes? Well, why does running a fever pose a health risk to you? It might impact your enzymatic reaction. Why is being cold for a prolonged period a problem? That may impact your enzymatic reactions. So you're going to pick those temperatures. You're going to write a biologically relevant hypothesis. What I mean by that is a hypothesis that has to do with temperatures that yeast or other organisms might actually experience on the planet. So we're not going to, so that's why I gave you a range from 0 to 60 rather than say, like, go to 200 degrees. Like, well, unless you're in an oven, you're not going to experience that in biology, right? Room temperature, I'm going to go ahead and tell you, your lab manual tells you to decide what control is. I'll just tell you, 60 degrees, I'm sorry, 60, but room temperature about 20 degrees is going to be your control. It's just, that's what yeast would be experiencing if they were in the room, right? So that'll be our control. Maximum temperature is 60, well, technically 63, because you can go plus or minus 3 degrees from that when you're trying to get it there. Why did I pick 60 as the biologically relevant heat? Because 60 is just a fuzz hotter than the hottest temperature recorded in Death Valley, which is the hottest temperature known on Earth, not counting like in a volcano or something, but the hottest terrestrial temperature. And you can look this up and put it in your second lab report, because this lab today will be lab report number 2, even though you haven't turned in 1 yet. I'll talk about that in a bit. The thermal maximum, and that's probably not even quite the right word, the lethal temperature for yeast is somewhere between 55 and 60 degrees. And it's not just because catalase may or may not denature. It's, you know, a lot of enzymes might have problems there. So pay attention to that target range, because we know, and what's funny is I tried to find this, like what temperature does yeast die? I tried to find this today, and I just did a quick search, and I found a whole bunch of sites that told me this information, but they were all cooking sites, like baking websites. So if you can find a scientific paper that cites that, I'd be interested. But it was funny how this came up in all the food websites. But they all said around 140 degrees Fahrenheit, which is about 60 degrees Celsius. So there's the organism we're looking at. That's yeast. They're single-celled eukaryotic fungi that reproduce a lot of times by budding. They split in half by mitosis and reproduce that way. They're found all over the environment as well, but we're looking at bread yeast. So the way to do this, now let me try to talk you into how to do this without messing it up. Okay, so you're going to have cold temperatures and hot temperatures and room temperatures, right? Okay, so to get things cold, you can't use a heat block to get something cold. Like you can't use an oven to refrigerate something. So I've had students try that. It doesn't work. We have ice in the back of the room in that white cooler. You can make an ice bath. That's when you put water and ice in one of your big beakers, and you can stick test tubes in there. And you can, each bench has one temperature probe that hooks to your computer and one thermometer, like a regular old school thermometer. It's an alcohol thermometer, it shouldn't be mercury, but we have one of each. So the reason I have one of each is so technically, this is easier when we have labs of groups of 4. Technically, if you are on the ball, you could be warming some up while you're also cooling some off and run them at the same time, you know, have thermometers in each. That might be hard with groups of 2. I'll pair you 2 up today, by the way. So what you're going to do is you're going to have to think about your design, because the way I envision this is you're going to cool and heat yeast and peroxide. One way that students mess this up, sometimes students go, oh, okay, I have to cool off this yeast and this peroxide. So I'll mix them together in a test tube and put them in ice. Don't do that. The reaction's done before you even cooled it off or warmed it up, right? I've had that happen in lab, so don't do that. You're going to have a test tube of yeast. If you remember, does anyone remember how much yeast we used per run from the last time? 2 mils. You have 2 mils of yeast in one tube, 2 mils of peroxide in another. That'll be for like run number 1, R1 on your data collection table, right? You can put those on ice and put a thermometer in the yeast. Let's just use the yeast as the one that we put the thermometer in. And you can watch as it cools off. Maybe about a minute later, 1 minute later, you can put the next set of test tubes in the ice bath for run 2. And then about a minute later, put the test tubes in there for run 3. So when yeast in this test tube that you put in there first get to the right temperature, you can assume that the next set will be ready in about a minute. And then the set after that will be ready in 2 minutes. Okay? Because we don't have thermometers to put in every single test tube. But then what you can do when this is incubated for a minute, you can pour the yeast or pour the peroxide into the yeast while it's still in the ice bath. You're gonna take the thermometer out, of course. You can pour the 2 together, put the stopper on, and record the data just like you did last time. Then, after you've done that, you'll know that when a minute has passed, the next set of test tubes is ready, and you can do that one. Okay? So that's how I envision you doing this, because the problem is if you put all these in at the same time, and then you run these 2, then you run these 2, then you run those 2, by the time you get to the last set, they've been in that ice a lot longer than the first set were. So we're trying to treat everything the same. And the way to help organize that, if you choose to use it, on page 43 is an incubation table. So it looks a lot like a data collection table. But the way that you would use something like this, and you can make it bigger, you can, you know, if there's not enough there. This is just for you to see how they work. Just to show you how it might work. So let's say temperature, degrees C. Let's say you're doing 0, not 0, but like 5, 10, 20, 30, etc., whatever. Replicate 1, let me get this right. Replicate 1, replicate 2, replicate 3. And then this is further divided into time in and time out. In, out, in, out. So if you know that this one reached temperature at 210, then you're going to need to pull it out at 211. And if you put this one in at 211, you know it'll be ready to come out at 212 or whatever. So you can keep track of when things need to be going in and out. Now, I've never used one of these in semesters where we've only incubated for 1 minute. Maybe it's not as useful as when we did it for 5 and students forgot when things went in and out, but you can try it, okay? That's what an incubation table is to help you keep track of when did this go in, when does it need to come out, and then you can keep track of several at once if they're all incubating at the same time. Okay, now the heat blocks. The heat blocks, I have a video on how to run the heat blocks. In case you want to look it up on your phone or something while you're doing this. The heat blocks are a little unintuitive, but the first things first, and TAs, I added this to the bullet list on the one online. You always want to add a couple milliliters of water to each of the wells in the heat block before you use it. The water in the wells will help transfer heat from the block to the test tube. Okay, so you'll put a little bit of water in those wells. You're going to turn it on. You're going to hit set calibrate. Then you got to always wait for it to blink. Then you're going to push shift. You're going to move the shift button, moves the decimal places, and then the up and down arrows change the temperature. And then you have to wait for it to stop blinking. You have to stand there and wait because it won't do anything if you're impatient. Then it'll stop blinking. Then you press start, and you'll see that the little green light will come on. That means it's working. I highly recommend you start with let's say you're doing, like I said, like 20, 30, and let's just say you're doing 60 after that. I would spread them out more if I could. But anyway, if I was doing 20, 30, and 60, 20 is room temperature, 30 I would do first with the heat block, and then I would do 60. The reason being, if you do 60 first, it's going to take it forever to cool down to 30 when you're done. Okay? So start with the coolest temperature that you're doing with your heat block and work your way up. And the good news is then, let's say you wanted to do 30 and you're trying to get it at the right temperature and you shoot past 30, you get to like 38 and you're like, crap. Well, then you can go ahead and use it for 60 and you can wait for it to cool down when you're done. So that way, if you start cool and work up, it's better. We have a lot of tips in the manual today. It's going to be important that you check out pages 42 and 43 and read through those while you're planning what you're doing. There's a place for a hypothesis, etc. as well. We recommend, for example, let's say you're testing 60. We recommend you set the heat block for 10 degrees warmer than that. Put your first test tube in, so on and so forth. And when that first test tube's getting close to 60, then you might reduce the heat to the heat block actually down to 60 so you don't shoot past it. But if you put it up at 10 degrees warmer, it seems to warm up faster than if you just set it for the actual temperature you're trying to achieve. So just a few tips that I figured out while playing around with it. If your test tubes begin to overheat or get too cold, you can pull them out of that heat block. Make sure you also check that test tubes are not gross. These, for example, have some crap in them, or water at least in them yet, so you might want to clean those out and yell at the last lab to talk. Where's that table? You might make sure your equipment's clean, make sure you don't mix up your pipettes just like last time. You want to make sure you don't get your yeast pipette mixed in with your peroxide pipette. But your basic hypothesis for today is going to be temperature and then catalase activity. So, is it going to speed up as it heats up? Is it going to speed up and then plateau? Is it going to speed up, plateau, and then crash? What do you think is going to happen? That's what you'll want to think about when you're predicting. And one last thing, when you do go to collect your data, remember last time, you click collect data about 5 seconds before you mix the two things together so you have a flat line. When you put the cork on, it's going to make a little bump. You don't want to count that initial cork going on as part of your data. And then you'll get a slope of the first several seconds of the reaction once it begins. So things to think about when you're doing that. All right. When it comes to the temperature probe, I'm going to have you go to the lab website again and download the template for Enzyme Lab 2. That'll set it up in the proper format. And then we're going to plug the temperature probes into channel 2 on your LabQuest unit. You're going to click insert at the top of the screen, then you're going to click on meter or hover over meter and then click digital meter, and that will add a readout of the digital thermometer onto your screen.